hello everybody. Thank you very much for joining us here today. This is 9 Connects, and you are here, you're in the right place if you are here for our webinar on buck converters without bucking the FCC, or our formal title, DC to DC switchers, problems and solutions. Our presenter today is Sean Kelly, who's had quite a bit of experience with power switchers, in addition to working with companies to get their products under FCC compliance. And to be perfectly honest with you, without further ado, let's get this beginning. So Sean, I'm going to turn the comm over to you.
Okay, thank you very much, Paul, for the introduction. So just a caveat out here that we were going to do a one-part type of presentation today, but really to do you all some justice, we decided to break it up into 2 parts. So I'm sorry if part of the material that you were hoping to hear today is not available today, but it will be available next month. So we hope that you'll sign up for that. In today's lesson, we're going to talk about basically what a DC-DC switcher design is, give you some practical understanding of how the switchers work, and specifically today we're going to talk about a buck regulator. That's one of the more popular ones that you all are going to be using. We're also going to talk specifically about some layout issues and guidelines. We're going to talk about, show you some perfect examples of what not to do and some examples of what to do. Now next month, we're actually going to do part 2, like I said, and in that one, we're going to actually do the introduction to the FCC requirements of a product and explain the testing procedure, and then explain the impact that can be that can happen if you don't properly lay out your board. We're also going to do a little intro to boost converters, because that is one of the other types that gets used. We're also going to talk about load regulation and efficiency. And as always, if you're interested in learning anything more about this presentation or other presentations that we've done in the past, please feel free to reach out to us through email, and we will get you some information. So before we get started, we'd like to get a poll asking you all kind of why you're here. So if you don't mind, just answer this. Give me an idea of why you're interested in this particular webinar. Okay. So 69% just want a better understanding of buck regulators. Okay, that's good. And for our loyal listeners, thank you very much for 30%. Loving our webinars. So why do you need a DC regulator? This may sound pretty basic, but ultimately what it comes down to is you have a device that needs 1 voltage, but you don't have that voltage coming into your product. Either you got a wall pack, or you're plugging it into the wall, or there's some type of source. You have to take that input voltage and you have to create another voltage from it. So that's why there's all these different types of regulators. They generally, in this situation, when we're talking about regulators for this webinar, we're going to talk about 2 specific types. The first type is a linear. You're probably already familiar with the linear regulator. It's basically just a variable resistor. And with that, you can see the little diagram down there with a variable resistor. All it does is turn the wasted energy into heat. The nice thing is it's simple and easy to implement. The other thing is it generally will create very low noise and therefore not present any EMI issues. But the downside is it will waste energy. Now, obviously, if you don't have to drop a whole lot of voltage, then it's not as wasteful. It's always a balance between how much energy you have to dissipate in a package and if you have the energy to waste. But they are super convenient to use. That's why so many people use them. So the second one, if you'll notice in the bottom, is a new diagram, is a switcher circuit. And a switcher circuit tries to help keep from wasting energy. The problem is it's difficult to implement. Not so much now as it used to be, but it's definitely more difficult than just a linear dropout regulator. But they can also be very high efficient, typically above 90%. The big downside is, besides the fact that they are more real estate on your board, they can create possible EMI concerns. So the two different types of general switchers that we're going to be talking about today is a buck, and a buck converter is used to decrease the voltage. So for example, if you've got a 5-volt USB and you need the 3.3 volts on your microprocessor, you would use a buck. The second one is a boost, and it's designed to increase the voltage. For example, you have two AA batteries, so you have 3 volts, but you need a 5-volt backlight on your display. You would use a boost circuit. Both are going to have the same basic elements, but they're going to be configured differently. And if you'll notice, I've got in here the little yellow outlines. Basically, you have an input capacitance, which you have on the left here. You have some type of switch mechanism, and you have a diode, sometimes called a catch diode, sometimes just referred to as a rectifier. You have this inductor here. This is going to be a key player in this. And then you have your output capacitance. So exactly how does a buck regulator work? Basically, it's a two-step system. Since we are stepping down the voltage, we can time splice those two steps. During phase one, the main idea is that we're going to let the inductor act as a pass-through device of our source. So if the voltage coming in has this input capacitor charged, when this switch, which we have denoted as a FET or Q, turns on, we're applying that input voltage over here to the inductor. That inductor then will ramp up its current, and building up a field will allow the voltage to be applied over here on the output capacitor. In the second phase, that same inductor is now going to become the source. And using the concept of positive current flow, the idea is that the current that was going through L at the beginning, the first phase, is now in the second phase going to continue going in that same direction. It just creates a different voltage potential. Because of the way the field collapses, when the field collapses, the voltage polarity changes. So let's look in detail on how the buck regulator works. In phase one, like we said, Q is turned on. So if you look at when Q first turns on, this node right here in the top between Q and L is going to be, say at the beginning when it's when you first turn it on, then this, sometimes referred to as an LX or switch node, it's going to be at a low potential. And so this voltage is going to come in through the switch, and it's going to pop that node up very quickly. And that's what you see on this leading edge over here during this on time. And then as that potential tries to drive current through the inductor is now going to allow that current to go through and ramp up. And during this time, you'll notice that the current going up is ultimately going to create a voltage on this output capacitance. In this phase one, the idea is you're charging the field in the inductor, and you're charging the voltage across the capacitor on the output through the IL. This is what we refer to as a power switch loop. And this power switch loop is going to dominate during this particular action. What I've shown you here in this graph is a typical switch circuit. Right here on the bottom, you'll see in light gray, this would be the switching activity. You'll notice that during the blue, I'm trying to keep colors consistent for you, is that during this charge time, this leading edge right here happens very quickly to get the current to flow during the inductor during this on time that you see at the top of the switch signal. And the way they generally work in overall is that when the voltage on the load gets to some preset minimum, whatever the switcher is designed to monitor and make a decision, then that switcher is what turns on that FET. And when it does, it increases the current through L. The equation that you're going to be wanting to understand is that the change in current per unit time is a function of the difference in voltage across the inductor and the inductance itself. This rate of increase, being a function of L and the change in voltage, is going to be problematic for you because it is this super fast rate of increase on the leading edge of these switches that's going to be creating all your problems. Now, as we change or create this leading edge of the switch signal, you're going to have to deal with this loop area that we're going to be talking about with the blue. And we're going to give you examples physically in the real world of what that blue circle is physically, how it's implemented. And it's going to be controlled ultimately by the physical locations of your capacitor on the input, the switch itself, whether it be an IC or FET, and the inductor, and then the output capacitance. When V out reaches the V max that the switcher is designed to create, then the switcher will turn off. Now we enter phase 2. In phase 2, the transistor is off, or FET is off. In this situation, once the switch opens, now you've got a magnetic field that is sitting inside the inductor that has energy stored in it. When you disconnect Q, that field no longer has a driving source, and so that inductor now starts to let the field collapse. And that energy that was stored in the magnetic field now creates current going in the same direction that it was going before. In this situation, that current is going to go through what we call the rectifier loop. That rectifier loop in orange is going to be dominating in this second half of this time frame. Again, you'll see that the down arrow in our diagram is indicating that the current coming through the inductor is decreasing because it was a stored energy and it's being used up in order to create a voltage on that output capacitor. And then all it does is it continues through that cycle over and over and over again. The interesting thing about this particular loop is the sudden change in current that you're going to have through the diode is what you're going to be concerned about, because you already had current going through the inductor. You already had current going through the output capacitance, but you didn't have current going through the inductor or the diode. Now you do. Again, the field collapses to create that current loop. We have the loop defined specifically by the 3 components that you see in that orange loop. So loop area, what is all the hubbub anyhow? First, the loop areas involved with the power switch loop and the rectifier loop are both involved with high DI-DT switching. In other words, very fast transients of current taking place. When you have high transients, that result is the same thing as high frequencies. So in this particular example, we're actually looking at a real circuit, an ADP 2300 running at 1.4 megahertz. Notice the switch signal itself has a very fast slew rate. If you'll notice on our timing diagram, the gradical is 400 nanosecond spacing. So 400 nanoseconds from here to here means that this switch is actually occurring in a whole lot less than 400 nanoseconds. Unfortunately, your data sheets, they don't typically specify the slew rate. In older circuits, 1 to 2 nanoseconds would have been pretty typical, but now they run even faster than that. So the question is, how is this going to help us understand what the problem could be? Well, in order to understand the implication of rise time, we need to look at the frequencies of concern based upon the rise time calculations. This is a very common diagram that you'll see on the left-hand side with a very common equation where the frequency of concerns that could possibly be generated is a function of this constant K on the left-hand side divided by the 20-80% rule of transient rise time. So you may be familiar with this formula, and you probably already know that typically people use a 0.35. But the interesting thing is, even at lower clock speeds, there are going to be higher order frequencies that can be of concern because it is the high frequencies that create the sharp edge of the signal. If you remember back from some of your basic introduction to square waves, or if you've been in our previous webinars, we talked about how a square wave is made up of the fundamental frequency and odd harmonics of that. So generally speaking, we think about the fifth harmonic rule over here on the right-hand side. We think that, okay, if I've got a rise time of, let's say, 100 picoseconds over here, and we use the 80-20 rule, then we're only worried about a maximum of 10 gigahertz. So anyhow, the main thing to keep in mind here is that, generally speaking, for faster rise times, K equaling 0.5 is very good for slow signals and fast edges. And I'm going to give you a perfect example. So let's say we have a switcher switching at 1 megahertz, and that's its operating frequency. So you see on the right-hand side, we've got this graph. Here's our operating frequency. So if we use a third and fifth harmonic, so you can see down here, we got 3 megahertz and 5 megahertz. You would normally think, okay, there's the 7th and 8th, 9th harmonic, that you might only be concerned about that harmonic content. Well, in fact, if I have a 0.1 nanosecond rise time, now the knee frequency is much greater than that fifth harmonic base frequency. In fact, if you take 0.5 and you divide it by 0.1, you end up getting a knee up there at 5 gigahertz. So all this energy you see up here at the very high frequencies is energy you may not be aware of that exists in your circuit if you have very fast slew rates. So in this case, let's just look at a 2 nanosecond rise time on the same 1 megahertz clock signal, which is today is pretty slow rise time. You can still have high frequencies all the way up in the 250 megahertz range. Why is that a concern? Because 250 megahertz is a lot shorter wavelength than what you might consider for the third, fourth, fifth, third, fifth, and seventh harmonic radiating signals. So now, what does this have to do with the loop area? From an EMI perspective, the frequency of greatest concern is not that of the switching clock. Like we talked about earlier with the 1 megahertz clock, that's not the big deal. It's the frequencies caused by the rising and falling edges. And it's this loop area that we're going to talk about that's going to dominate the ability of radiating these signals. So the board layout is going to be the most critical element in controlling this EM radiation. It's also the same thing that's going to be affecting your mitigating any behavior of aggressor on victim traces. So now, why is the loop area so dominant? How does it create a problem for us? So there's two aspects I want you to consider. Horizontally, in other words, in the plane of the board, then what I'm showing you here is an example of, here's my input voltage, and the input voltage is going to go into the switcher, and it comes out of the switcher through the inductor, and it's going to go through the output capacitance, back through ground, and it's going to come back through the input capacitance again, and so there is your power switcher loop. Now, in this case, there is no catch diode. The diode is actually part of the inside the chip. That happens sometimes. The other aspect we can have is a vertical loop. So here's a representation of that same circuit. In this case, if they didn't have the proper ground port located between these two capacitors that you see here on the top, then if they used a via, and let's say the return path was on the bottom of the board, then now my return currents are going through the via to the bottom of the board, back up through the via, and through these input capacitors, and back to my switcher, and back through the inductor. So now I have circuits, current flowing in a vertical direction. So now, why do these loop areas, how do they work? So we're going to talk about a term called magnetic flux. Magnetic flux is used or is described by this equation: phi equals AB cosine of theta. And in this situation, we have over here on the right-hand side, the B field is your magnetic field created by your by something that's carrying current. And we're trying to understand, how does this flux relate to this loop area? So in the equation, we're worried about the size of the loop area, the strength of the magnetic field within that area, and the angle between that loop area and the B field. So let's give an example. If the loop is perpendicular to that magnetic field, in other words, the loop is sitting here in this direction and this black line was horizontal. If you did that, then you think about the fact that the B field is not going to be going through the loop, which makes sense. So this angle is 90 degrees. Well, the cosine of 90 degrees is 0. So therefore, if the cosine of 90 degrees being 0 means phi is 0. There's no magnetic flux. But if the loop is parallel to the magnetic field, then that angle is 0. Now phi is only dependent upon the loop area and the B field within the loop area. Now in a switcher circuit, you're going to assume that the B is a value that you can't change. It just is what it is based upon the behavior of the circuit. It's not necessarily a constant as in it never changes. I'm just saying you can't control it because it needs to be the current that it needs to be in order to generate the voltage out. So in that case, now phi is directly proportional to the loop area. So if we increase the loop area, then we've increased the magnetic flux. Why is the big deal about that? Because if we change the magnetic flux over time, because of Faraday's law, that induces a current. If an aggressor loop area increases, the magnetic flux can increase, and the result is you have increased induced currents in victim traces. So I want to ask you another question, if you don't mind helping me out. Generally speaking, magnetic flux can be reduced by... Okay, good. All of the above is the answer. And I worded this so that you all understood this is generally speaking about how the loop area and the flux works, not specific to just switchers in general. So sorry if that may have been confusing to anybody, because I do see that quite a few of y'all said reducing the loop area. Okay, so the next thing we want to talk about is priority and focus of your circuit. And the first thing we want to talk about is the power switch loop, and then the rectifier loop will be next. The output loop itself, which is between the output capacitor and the load, is usually not as dominating, but it's definitely something you want to consider, especially if your load is far away from your output capacitor. Then we're going to look at the layout. The layout, you really want your components to be physically close, because ultimately your loop area is a function of how far apart they are. When you get them close, then you're going to want to focus on trying to get your traces as short as possible and as wide as possible. Then your secondary focus is going to be on the input loop. That input capacitor has got to get energy from the power supply. That, again, is usually not nearly as problematic because it's at a higher voltage, and so it doesn't have to have as much current coming into it in order to provide the switcher with the energy it needs on the output. And then lastly is the feedback network. The feedback network is what the switcher uses to determine when to turn that switch on and off in order to keep the voltage within this min and max range. If you don't have that feedback network routed correctly, then not only can you make your switcher noisy, but you can also make it susceptible to other devices, might influence the way the switcher is behaving. So one of the things we want to do is talk about reducing the probability of radiation. And you can do that by reducing the overall inductance in the loop path. Remember, the only inductance you really want is in the inductor. Now, there are two types of inductance. The self-inductance is what we're talking about first. Mutual will be next. And self-inductance is probably what you're more familiar with. That is what we talk about when we're talking about, let's say, a piece of wire. And we're going to get into a specific example that just a piece of wire just sitting on the table, 5 inches long and let's say 10 mils in diameter. It has a known inductance. And that is based upon the cross-sectional area. If you increase the cross-sectional area, the inductance goes down. You can think of it just like a resistor, that when an area of the cross-sectional area of a wire gets bigger, the overall resistance goes down. Length, when the length decreases, the inductance goes down. So if you have a piece of wire that's 1 inch, it doesn't have as much inductance as one that's 10 feet long. Both of these respond very similar to the concept of resistance. So if you're ever trying to change a trace on a board and you're trying to remember whether or not you're increasing or decreasing inductance as you change the width or the copper height, then always think about it as if it were a resistor. Now let's just take a typical via that's on a 62 mil board. A lot of us use just 1 ounce copper on it. And if you pick a hole size of 8 mil, the interesting thing is it's going to have the same self-inductance as a wire, only 1.4 mils wide or diameter at the same length. Both of them have a self-inductance of 1.4 nanohenries, which you may see the irony in that 1 ounce copper is 1.4 mils thick. So it's easy to remember that an approximation of your via inductance is going to be 1.4 nanohenry on a 62 mil board. Now we're going to talk about the second type of inductance, and that's mutual. Mutual inductance is broken down into two different types. Aiding, which you can see on the right, is when you have two inductors where the current's flowing in the same direction physically, and the windings are set up so that they are in the same direction also. In this case, the inductance is controlled by M, or influenced by M. The second one is opposing. In opposing, the wires are in an actual coil would be wound in the second coil opposite direction from the first coil. In both of these cases, the current is going in the same direction. But you could, and I'm going to show you an example, think about it as if the windings were in the same direction, but the current was going in the opposite direction. That would also be an opposing situation. So let's think about a basic circuit when the coupling coefficient is 0. When M is equal to 0, the calculation of your parallel inductors is basically the same format as parallel resistors. You may have remembered this from your introduction to circuits. But when M is not 0, the parallel inductors have a totally different inductance. So let's talk about aiding. In an aiding situation, here's your equation over here. And remember, we said if M equals 0, it was basically like parallel resistors. So you had, in parallel resistors, it would be R1 times R2 over R1 plus R2. Well, it's the same thing with parallel inductors. These two terms would cancel out. And I gave you an example down here where we have a bunch of ground vias underneath the IC. We have them underneath, and we have them to the left, and we have them to the right. Now we're going to take specifically two vias used for current going in the same direction through the vias. Now remember, each of the previous vias we talked about had an inductance of 1.4 nanohenries. And with no coupling, because of the parallel equation, then we know that because they're the same inductance, then the total inductance is only 1/2 of the individual inductance, so 0.7 nanohenries. The interesting thing about them is as the spacing between them will decrease, then the coupling increases. When that coupling increases, it actually makes the total inductance go back up. In fact, you can get it, if they were right next to each other, you would get almost the same inductance for both of them as you would for just one. So the conclusion here is when you're using vias to change layers, don't put them too close together. You need to remember that the goal is to maximize separation while having enough vias to carry the current. So you don't want to put them too close together, or else you're creating excess inductance. Now, in an opposing situation, similar equation, but I want you to think of currents in a board plane. And what I mean by that is, let's say you have a power coming into a circuit on the top layer, and then right below it, you have the return current. So it's going back to the source. In this case, you want to maximize your coupling, and you do that by physically placing the two layers in your board close together. Because when you do that, as M approaches L, then your total inductance is going to approach 0. So let's show an example. If we take opposing vias, and I used a calculator online for this, and you can go to this website, and we have links for you. And I put these things 1 inch apart, and I set the mu to 0.153 to give you approximation of 1.4 nanohenry, 2 inductors in parallel, giving you a total inductance of 0.7 because they're 1 inch apart. See down here, I have 1,000 mils separation. The interesting thing is, if you notice that if now I put them close together at 100 mils, now my inductance has dropped. Now instead of being 0.7 nanohenries, it's 0.478 nanohenries. If I increase the coupling even more, now it drops to 0.411 nanohenries. And when I get to 15 mil spacing, it's dropped down to 0.95 nanohenries. So let's talk about specifically if you have traces on your board. Let's say you have a 50 mil trace on top and a 50 mil return on the bottom. So now my trace separation height-wise is 63 mils. If I do that, you'll see that my inductance total is 4 nanohenries. But if I move the return path up just the second layer right underneath it, and I only have a 3 mil prepreg between the two layers, now my inductance for that same set of traces is only 0.192. That's a huge decrease in inductance. That's also when you start doing complicated board stack ups, just a side note, and you're trying to provide power to high current devices like an FPGA, you're going to want to have power and ground very tightly coupled in your board stack up and close in layer count to your load, just for this reason. This is part of the reason, I should say. Now let's do a little review of exactly what we just tried to cover, because I know I covered a lot of material. If you're going to use vias as a mechanism for multiple current paths to reduce resistance, then be aware that there are high DIDT transients, and they will see a higher inductance than you might expect if the vias are too close. For example, here's one. If I have a 7-volt circuit and I'm trying to put this into a power plane, my switcher's on the top, obviously, and I'm trying to put this current path into the board. Here's a couple of vias that somebody put into this copper pour to go into the board. A better way to do that was to separate the vias. Now I've reduced the mutual coupling, and therefore I've reduced the overall inductance. So now there's not as much impedance of that current to go into the power plane. If you're going to be using vias or pours to handle opposing currents, for example, let's say you have a decoupling capacitor or routed power, then you want to maximize the coupling to minimize the total inductance. Here's an example of a decoupling cap. If you have power coming into the decoupling cap and the ground via, you want to put those vias as close as possible together, and therefore your overall inductance of that circuit has dropped. Some other approaches that people use are parallel capacitors, especially on the output. And the reason being is that if the capacitors are identical, you're doubling the capacitance and lowering the ESR. Now, obviously, they don't have to be exactly the same capacitor. In fact, usually you'll see a multitude of different variable capacitors because each one will have an ESR at a different frequency. That's another whole conversation that we could spend a long time on. The nice thing about having a lower ESR, though, is it allows for less heating for any given ripple voltage. One of the things that you'll need to be careful of is you don't overheat that capacitor if you have too much ripple voltage for your capacitor. It also is obviously going to minimize your inductance to the ground loop because now you have 2 paths to the ground. The other thing you want to think about is your inductor itself. You want to make it the lowest profile possible and make it shielded. If you shield it, you're minimizing the magnetic fields being radiated. And obviously, since we're talking about loop area, well, then you need the smallest footprint. So in closing this section, I want to bring this up because it is important for you all to understand this. Data sheets are typically written by either junior engineers or engineers that are non-layout experts. Sometimes they can give you bad recommendations on the layout. So don't always assume that the data sheet is giving you exactly what you need. Just be aware of the proper techniques and then take the recommendations with a grain of salt. And if you see something just seems really weird, then just take the time to research it. So we have another polling question for you. This will be an easy answer, just a true and false. The power switch loop is more problematic than the rectifier loop. Okay, looks like we've got 67% said true. Okay, I agree with you. It is true. And the reason being is that you have a greater loop area. And because that greater loop area, you have a greater possibility of transmitting that magnetic field into things around it that can either act as an antenna and radiate the signal out of the board, or it can induce noise into victim traces that are anywhere near it. Great job. Okay, so here's a sample layout recommendation for the ADP 2300 that we were talking about before. They were nice enough in the data sheet to show you in blue here your high current traces. Here's the pinout of the part, and then if you'll notice over here on the right. So let's look at the power switch loop first. So here we have the input coming in here on the bottom. So here's your input capacitor. So VN comes in through your switcher. It has an integrated FET, so you don't have to worry about the FET itself. It's inside. And then you have this switch node coming out here, which is shared by your catch diode and this little feedback cap. And then also here it is on your inductor. So the output current goes through your inductor to charge your output cap. And then here's your return current in blue back to your input. Nice tight loop. There's no way that could make that ever any smaller. So that's good. Let's take a look at the rectifier loop. Same thing. Now when the inductor is trying to discharge, keeping this output capacitance charged, then again, the return path is back through the catch diode. That is as tight as you can get it. So the question is, why am I bringing this up? The only thing I would change is the feedback path. Notice what they have over here on the right is the feedback path is going all the way around this circuit over here. When in fact, what I would recommend is running it right off of here. There's not going to be a significant amount of voltage drop between this point here and this point over here to change your output voltage. So I would have run it over here, swapped your resistors, and had a very short feedback path. Yep. So if you'll notice though, on this diagram, here's your switcher circuit. Pin 2 is your ground. Notice that they only have two little vias here. So when you're looking at this, you may ask yourself, why in the world do they only have two little vias? So while you're contemplating that, let me know what you think, why that might be the case, why they might have done that. Okay, good. The majority of you all got the correct answer. 44% got the ground pins are not part of any high current loop. Remember, we said the problematic part of regulator designs is the high current paths being spread out to create large loop areas. Well, the ground pins on this IC, and let me put a caveat here, on this IC do not carry large amounts of current. Some of the more recent regulators actually do have a lot of current coming into the package. So you got to be careful of that. So I want to end this with, here's a circuit that was on a board that I was having to review. And this circuit was done by a company, $1.4 billion company. So the interesting thing is, when I saw this, it amazed me as a company that big can create a switching circuit like this. So it just goes to show you that everybody makes mistakes. That's for sure, no matter how big a company you have. Okay, so do you see any problems? Now this was on the bottom of the board, so it was in blue, and I use blue arrows to denote the power switch loop. So what I did is I changed the picture so that I used some arbitrary color for the copper pores. So what we have here, here's your input voltage and your ground. So this is your input capacitor. Your switcher's in the middle. Here's your catch diode or rectifier. Here's your inductor. Here's your output capacitance. So here's your current loop for the power switch loop. Your VN comes in through this trace. It comes in, goes back out of the switcher, comes to this little teeny weeny trace, come over here through the inductor. From the inductor, it goes to the output. From the output, it goes through the output capacitor, back through the ground, back underneath the switcher, and then back through C16, the input capacitor. So quite a path there. It's pretty large. Let's look at the rectifier loop. Okay, so when the inductor here in the middle is discharging, you can see that the path through the diode Actually, the arrows are backwards. My apologies. I should have shown it this way. So again, the current's trying to flow this way through this capacitor, back through the pore, back through your diode, and back to the inductor. Again, very large loop area. So in summation, you want to minimize your loop area. In doing so, you're going to reduce the aggressor type of behavior on any nearby circuits. You're also going to decrease the likelihood of creating antenna, again, because if you're switching at very fast slew rates on your switch node, then those high DIDT situations create very high frequencies. Those very high frequencies have very short wavelengths. Short wavelengths means that you can have traces and pores and openings in the pores. All those can act as antennas. You also want to minimize your path inductance to help minimize any unwanted coupling and increase efficiency. The two main loops that you're going to be concerned with, the power switching, which is the big blue one from input to output, and then the rectifying loop, which is through the rectifier diode. Remember, the rate of switching is more of a problem caused than the actual switching frequency itself. So it's the leading and trailing edges of the switch signal that end up causing all your problems. Now, part 2, a little teaser for next month. Go a little bit more into what we're going to cover. We're going to talk about boost converters. We're going to talk about how the DC switcher itself can be a source of failure for EMC compliance due to that switching noise. And we're going to do that in a couple ways. The first one is how we can fail at the conducted emission source. The conducted emission basically is you're looking to see if your switcher is putting noise back out on a power line. And the second side of this is we're going to look to see if any of your structures are actually radiating unintentionally a signal because that structure acts like an antenna. We're going to actually equate you with the actual FCC requirements themselves so you can know why and how much your device is failing. We're going to go into explaining the test procedure itself. If you've never been to a certified lab and watched them how to do this, then you'll be an introduction into that process too. Then we'll go a little bit into load regulation and converter efficiency. Most of this is controlled by the switcher itself. You don't really have a whole lot of control over it, but the efficiency, we can talk about what you can do to help keep the efficiency up. So that ends our webinar material itself. So we have one more question, if you don't mind. I'm always interested to hear your opinion on the material itself, because ultimately what I want to do is make sure I get the material geared toward what you're wanting to know. Oh, perfect. Good. I'm glad that I met so many expectations. Okay, well, with that, I will turn this over to Paul. He's going to talk to you for just a quick second or two. And while he's doing that, I'm going to read the questions that have been submitted. And well, I'll get back to you with answers. And those that I can't answer today, we will answer ultimately in a presentation, and that will be available also to you all who request it.
All right, thank you very much, Sean, for doing that. If you do have any questions, please do feel free to write those in so that it's just a matter of going to the questions panel on your GoToWebinar panel there and just writing that question in. That'll give Sean an opportunity to take a look at that. So while he is doing that, just a little bit about 9.Connects. You know, you're here for a reason, and for today, it was to understand the concept of the buck circuit. I know that it's always like drinking from the proverbial fire hose here, but hopefully you picked up some key points when trying to design or put together a buck circuit on your printed circuit board. And secondly, to minimize the radiating signatures. So yeah, we didn't have a lot of time to get into the FCC stuff, That was a conscientious decision that we made because we didn't want to rush through that here. But you can basically see that if you can remove these loops or minimize these loops, as Sean was discussing here today, that's going to certainly assist you when you actually do have to get into FCC testing. So hopefully those are the 2 points that you walked away with. What do we do here at 9.Connects? Well, we do basically 3 things. We do services, we do training, and we do consulting. But for the moment, I just want to talk about our services. And there's a number of different services that we provide. But in related to what we're talking about in our webinar here today, we are first and foremost getting into and have been doing some work in board simulation. We've had a lot of requests for this. We're seeing that with RF and the high-speed design stuff, this is being required more and more of our customers, and so we have been making headway into the board simulation aspect of it. And it's something that we're now providing as a service. Secondly, if you ever need help with power design, well, you can see that Sean has that knowledge here, so we're certainly able to assist you with that. And of course, with FCC compliance, obviously next month we're going to talk more about this. However, if you need assistance with it right now, Sean has been through the gauntlet, and he can certainly assist you with that. And of course, for other services as well. So it's always worth an ask, right? The worst we're going to say is we can't do it, but feel free to ask us. We really do try to think outside of the box when it comes to providing services to each and every one of our customers. More information, check us out at 9.connects.com. So we have a plethora of videos that we've done. Of course, all of our training services are up there, and of course, our design services are listed there.